Great. Okay, thank you, everyone. Wow, this has been a really informative day. I congratulate and thank all the speakers for terrific, informative talks. I've learned a lot. It's been a bit of a challenge to try to summarize some of what I heard. In addition to the great talks, what I saw going on in the room was a lot of side conversations, and I think that is probably half of or more of the benefit of this kind of an event, is to get the conversations started. So I think we've already been a success in doing that. All right, let me just begin with a very brief reminder of what our charge was today, to the objectives of the workshop, to bring together communities to discuss emerging technologies. And in particular, today we are focused on technologies for identifying and measuring plastics and understanding their effects. So that's what we'll deal with today in this summary. And what I did, I decided to organize this by first talking about the knowledge gaps and the challenges that I heard, both for identify and for looking at effects. And actually, that was the easy part. There were a lot of knowledge gaps, a lot of challenges. A little bit harder part was to come up with the emerging technologies and approaches, the solutions to filling those knowledge gaps. And so you'll be the judge of how well I did that. So I want to begin by talking about some misperceptions that we heard about. So this is an issue, as you know. Microplastics have caught the imagination of the public and the media. And when that happens, there's bound to be some misinformation and some misperceptions. And so we heard about some of them. The first we heard about is that the Great Pacific Garbage Patch is not a floating island of trash in the Pacific Ocean. And I think that bears repeating. I know Kara's been saying that over and over again in every keynote that she gives. But it's something we all need to keep in mind. Another misperception by some is that microplastics is just a single kind of a pollutant and we can treat all microplastics the same. And obviously, we know that that's not true, but when we use the word microplastics were found here or there, we're kind of falling into the trap of thinking about it as a unified pollutant, which it is not. Another misperception is that exposure is the same as risk. And I think we heard that several times today. Obviously, exposure is one component of risk, but exposure doesn't define risk, and you all know that. Another misperception is that what we do in the laboratory reflects what's going on in the environment. And clearly the environment has effects on the plastics and on the organisms that we can't reproduce in the lab. And so we need to understand the limitations of laboratory studies for addressing these questions. Another misperception is that seafood is the largest exposure source for microplastics in humans. And seafood certainly has gotten much of the attention, but as we heard today, there are both known sources that seem to be more important, as well as a number of unknown sources, so we really don't understand the totality of human exposure. Okay, now on to some of the challenges and knowledge gaps with regard to the identification and measurements. So as we know, and we heard many, many times, microplastics are complex and diverse. Complex means there are many different types, and diverse means the types can vary tremendously in terms of their properties, and so we need to keep that in mind. Another paralleling that, or on top of that, is another layer, is the complexity of the environment where the microplastics live, and that's important both because the environment imposes conditions that affect the behavior of the plastics, but also that the environment is composed of many different matrices, and that affects our ability to measure and to extract and measure the plastics in the environment. Something I think I heard Bart say was that the best method for measuring plastics in the environment depends on what your specific application is. And I think others echoed that you have to specifically choose your methods with a target goal in mind, and not all methods will be applicable in all situations. Sample preparation was talked about several times. It's a critical aspect of measuring things in the environment, but it's a non-trivial exercise. It's complicated and it varies by matrix. And so this is clearly one of the challenges that people face when trying to measure plastics in the environment. We heard a number of times about the lack of standardization, standard definitions, what is a microplastic, standard methods to extract or measure, and both reference and test materials that we can use as standards to unify, to make laboratory and field results translatable across different groups. And we heard that because of issues of lack of standardization and other deficiencies of this still young science, that many of the results that have undergone peer review in the literature may be unreliable. And there's more. Laboratory contamination issues, the complexity of dealing with additives, weathering in the environment, the cost and the time associated with analyzing plastics, and I'm sure I missed several of these. Okay, now the elephant in the room, and we talked about this many times, is the effective particle size on our ability to measure plastics in the environment. And I saw curves like this. I've seen curves like this in many papers. This one happened to be from a paper from Gunnar Gertz's lab measuring sediment and surface microplastics. And so you can see this is the size dimension here. And this shows what many studies have shown, and Bart showed in his talk very well, is that the number of plastic particles increases as the size gets smaller. And almost every one of the figures I've seen that look like this, they all end at 11 microns. 11 microns, that's a magic number. So the question is, what happens below 11 microns? And the short answer is that we don't know. But let me and we heard this many times, let me just reinforce it because I think it's such a key point in what we're trying to do. We know from work that Kara talked about that a lot of the data we have on plastics in the surface of the ocean and elsewhere sort of ends at this 330 micron point because plankton nets are designed to sample plankton were used to collect those samples. It makes a lot of sense. And the 11 micron measurement is around here. So what we don't know, and so this is a theoretical curve that shows the expected increase in particle number as the size gets smaller and smaller. We don't actually know if this happens. We don't actually know if in the environment the increase in plastics continue as the particles get smaller. That seems to me a really key question that we need to answer. And it's important, as you heard many times also, because it's the nanosize particles that are ones that are somewhat likely to be taken up across biological membranes. So the ones that potentially may impose the greatest risk to health of humans and animals. Again, there's a lot we don't know about that question as well. Okay, knowledge gaps in understanding effects of plastics. We heard about the multiple potential sources of human exposure, and we don't yet understand what they all are or what the relative contributions are. There's been incomplete sampling, in particular of certain foods that haven't been sampled at all. The nanoplastics problem rears its ugly head again here when we're talking about human exposure. Potential effects are not well defined, so the hazard of plastic particles is not well defined. We essentially know nothing about, very little about humans, aside from some work on workers. In wildlife, I heard the effects are equivocal. Some studies show effects, an equal number of studies show a lack of effect under the conditions of the assays. Experimental studies are fraught by deficiencies, including unrealistically high exposures, inconsistent types of microplastics, studies so that you can't easily compare across different studies done in different laboratories, and in general, a lack of quality control in the kinds of toxicity testing that has been done. Now, just an example of this, again, to drive home the point, there was a letter to the editor in the Proceedings of the National Academy of Sciences a couple of years ago, in response to a paper purporting to show effects of microplastics on, I think it was oysters, pointing out this problem with the literature that most of the studies are done at unrealistically high concentrations. And what this graph from this lens paper shows, again, the size dimension is here, and the concentration is here. These red points are the experimentally determined concentrations of these microplastics in various environments. The red line in the pink cloud is the extrapolated expected increase in particle number as the size gets smaller. I showed you on that previous graph. We don't actually know if this happens, but here is where all the experimental studies are being done. Several orders of magnitude higher concentrations than even the unknown but expected increased concentrations in the environment. So this again drives home the need to do laboratory studies under much more environmentally realistic exposure conditions. Okay, more knowledge gaps. Wait, I'm not done. Lack of information on bioavailability in humans, we heard that several times. We don't know anything about dose-response relationships in humans, yada, yada. Relative risk of microplastics versus other kinds of stressors are not being considered. This applies not just to humans, but to animals and the environment as well. And a number of other particle types that may potentially have important health effects are generally ignored. We heard about total suspended solids. Tire wear particles, I think, are getting some increased attention, and paint chips from anti-fouling paints. Okay, all right, that's very negative. Let's get into some solutions and see where we are with that. I heard from Kara, and I agree that we need to apply the best available science to to solving these challenges that we face with identifying plastics and their effects. Let's see. Bart talked about defining best practices, and he referred to the wisdom of the crowd. We might have some discussion about whether the wisdom of the crowd is the way we want to define best practices, but I look forward to having that over a beer, perhaps, Bart? Which crowd? Yes. Maybe the European crowd. We need to align our analytical approaches with the application. I think this echoes something that was on an earlier slide. I heard about trying to simplify this daunting complexity that we have with this group of materials. And Bart talked about using probability distributions to capture the habits of these plastic particles. And that seems to me quite a promising approach. Clearly, we need to implement quality assurance protocols throughout, both for analyzing plastics in the environment and analyzing their effects. We heard about proficiency testing, sending samples out to multiple laboratories so that they can gauge their success in measuring these materials. We maybe didn't have an explicit discussion about the question of whether we need to have standard methods that are prescribed or just performance standards, criteria that anyone using a particular method has to meet, that method has to meet, so that everyone doesn't have to use the exact same method. This is not an area that I am very experienced in, but I know there are people in the room who deal with these standardization questions. And we heard about potential for automation and screening tests that are under development, and these potentially show promise for helping us to prioritize and rapidly analyze samples that can then be subject to more detailed analysis. And we heard some promise, and we've seen some papers coming out recently showing emerging analytical technologies that can help us get down into the smaller particle range and generally extend our ability to make these measurements that we so desperately need to make. Okay, some more solutions on the effects side of things. I heard both from NIST and USDA that there are standard materials being generated that can be used for toxicity testing, for example, or as standards and analytical techniques. I think that was good news, in particular with regard to the nanoplastic size range. I heard the suggestion that we use defined mixtures of microplastics, the same way we do with particulate matter, for example, and there was some discussion about that in this last session that I didn't quite capture, but it seems like that is something worth thinking about more and pursuing. There clearly is a need to standardize the tox testing protocols and to better design animal studies to replicate the kinds of exposures that we expect humans will have if it's human health we're concerned about. And we shouldn't reinvent the wheel. There are lessons to be learned from people, as we heard, from people who were involved in nanomaterial toxicity testing, from the nanopharm, people working in nanopharmacology and nanomedicines, from worker studies that I hadn't been aware of, that really can help inform what we need to be looking at with some of these exposures, and lessons from mixtures toxicology, and there are a lot of experts in that. So I think with regard to the effects, it seems to me it's not so much about emerging technologies as it is about being smart and not coming up with things that have already been solved, or at least learning from the experience of other groups that have tackled similar problems in the past. Okay, so this is just an example of that. Another example of lessons from other fields. I have some colleagues who are environmental chemists, and they've made the point that what's going on with plastics is very much parallel the way the field of black carbon developed in marine chemistry. And they said the solution there was in the complexity of black carbon is, if not equal, close to that of the plastics problem. And they said the solution was to embrace the complexity and recognize that one size doesn't fit all. There's no silver bullet. And we're going to need to apply multiple kinds of approaches to really fully understand this complex problem. And then the nanotoxicology, nanopharmacology lessons I've already alluded to. I thought this was a very nice review from people with expertise in nanotoxicology with lessons about how to apply it to nanoplastics. Okay, I heard about opportunities for people to work together in a collaborative way to solve some of these problems. And these involve collaboration across sectors, industry, government, academia, NGOs, and across countries, US and Europe, in fact, on a global scale. Many of these have to do with harmonization, standardization, everyone agreeing on the best way to approach this. So I'll just go through some of these: performance standards, reference materials, interlaboratory comparisons. Are there intercontinental, international funding opportunities that we should be taking advantage of to better forge these collaborative ties across the pond and around the world? And there are other public-private partnerships. We heard some examples. We heard one from Jennifer on her partnership with the chemical manufacturers that really helped advance her work, and I think that's a great example of what's possible if we all work together to try to understand this problem. And I heard at the very end that we need to have a federal strategy for funding research, and I think that's a terrific idea, and I think that might be the last point, so I'll say it again. I thought that was a great idea to come up with a federal strategy for funding research so that the agencies are working together. And I'm pleased to hear that there's a federal working group that's meeting later this week, and many of the members are, I think, in this room or online. So maybe that will be a topic of conversation at the follow-up meeting. And I'll end there and say on to tomorrow, where we're talking about reducing plastics in the environment and some of the public health and policy implications. It promises to be just as interesting a day, so I invite you to all come back tomorrow morning refreshed and ready to learn some more. Thank you.